This is Physics 2212, Lab 3, where we are looking at circuits. So the lab objectives, the purpose was to predict the behavior of circuits containing resistors in series and parallel and use multimeters to measure conventional current. Please ignore the fact that I have pre-duct. Models V equals IR, which is Ohm's law, and then current in is equal to current out, and then potential difference 1 plus potential difference 2 plus however many potential differences is equal to 0, which is the loop rule. And then R series is equal to R1 plus R2 plus how many other R's in the actual series. So our discoveries is the current changes depending on the resistors and the capacitors, and we'll go more into detail later on, basically looking at depending on how many resistors you have, how much resistance you have, and then also how long you let a capacitor charge for. And then our system was the circuit, and then surroundings is not applicable because it's only a simulation. So our findings, this was the first circuit that was created where we had 2 batteries, which equaled a total of 3 volts, and then 2 resistors, which equaled a total of 147 ohms. So please ignore the 9. That's not supposed to be there. That's a 3. So the prediction from Ohm's law is V equals IR, and the resistors in series give us 147 ohms, and the total voltage is actually 3, not 9, and this gave us the current as 0.02 amps, which is the same as the simulation, and the second current is the same as the first because the circuit is connected in series. If it was connected in parallel, it would be different. And if the ammeter was backwards, it's supposed to read the current in the opposite direction, so instead of it being plus 0.2 amps, it's negative 0.2 amps. However, for whatever reason, I could not get the simulation to show it regardless of how I attach the ammeter, which is not how it's supposed to work, so I do apologize. And then the second part was the second part was connecting the voltmeter to figure out the change in voltage depending on the resistor. And if the voltmeter is attached in series, the circuit breaks and there is no current flowing through. So the voltmeter has to be attached in parallel. And this read the current through the voltage through resistor 1 is equal to negative 0.96 volts, and then R2 is negative 2.04 volts, which adds up to negative 3, and then the potential difference is 0, which is as expected based on the loop rule. And then the other checkpoints are measured to be 0 volts each, and the ammeter, when it was connected in parallel, was reading less current because I in is equal to I out. And then some of the lab findings included that and then in the next part with the capacitor, the light is bright but then slowly goes out as the capacitor is charged and then uncharged. And then when the current decreases to 0, that indicates that it's either fully or uncharged. And then it is 14.6 seconds until the capacitor is fully charged with the 10 ohm light bulb, and then 27.9 seconds with the 20 ohm light bulb, which in particular has a lot of error in it, and I'm sure. The last part asked us to calculate the predicted potential difference across the capacitor with a 30 ohm light bulb, which was found to be negative 9 volts, which agrees with the calculation of what the voltage should be around the capacitor. There's no code in this lab. So sources of error, yours truly is terrible at working a stopwatch. And then in addition, there's always potential human error in the way that I set up the actual circuits. So be warned. Then so our first question, what if you were doing this experiment in real life and used an actual ammeter instead of the ideal simulated ammeter? What's the difference about the real one and the simulation and how it would have affected? The real ammeter is dependent on how you orient it. And then also if the ammeter is connected and is analog, it's much harder to read and you have to use significant figures, which leads to more human error. And the ammeter also adds a bit of resistance, so it would decrease the overall current. And then another what if is if we used a real battery and a real capacitor with no resistance, how would this how does the ideal model predict it, and how does it look in real life? In our ideal model, the capacitor would charge almost instantly. However, in real life, wires have resistivity, so you would see it slow down, not a significant amount, but the charging would be slower in a real life model. Oh, thank you.